Welcome back. Now we'll be moving on to electrodynamics and relativity, which is chapter 12 in the textbook. The textbook poses relativity it frames it in terms of electricity and magnetism, and the most obvious case is Faraday's law. Because from Faraday's law, we saw that the curl of an electric field is related to the rate of change of the magnetic field. But we saw that when Faraday first observed this, that he could have some ring here, some loop of a wire, and he could move this magnet into this wire, and saw that that created a current here, or he could have this magnet stationary and then move this ring over the magnet. So the second case, moving the loop sees a change in the magnetic flux, and the change in the magnetic flux causes the current, whereas in this first case, the moving magnet induces an electric field, and that causes the current. So, but the EMF, the electromotive force, or the potential, is actually the same value either way. It's just related to the rate of change of this magnetic flux. And so he frames this, that this is kind of like the basis for special relativity, that it doesn't matter what's moving. If this is moving towards the ring or the ring's moving towards this, it has to have the same physics. Although people in the different frames, if you're in the frame of the magnet or if you're in the frame of the ring, you'll see different answers, or you'll come up with different physical reasoning as to why you get this. But having two different explanations for the same thing probably means that there's some link between these two. And that's his basis for explaining how special relativity comes about. I'm going to frame it as an experimentalist. I'm going to frame it more so in this terms of the Michelson-Morley experiment, where he had this massive block of granite. So this is an image that I got off of Wikipedia of his experiment, and I think this was in Cleveland is where it was done, so relatively nearby, but this is a slab of granite that I don't know how much this weighed, but probably several tons. This thing is just massive. And the light would come in from, I guess, here, and it would bounce off these mirrors. And this table ends up having some arms that are 11 meters long. So I think it might bounce twice back and forth, but I think this table must be something like 3 meters across or something like that. So about 10 feet. So it's a fairly large table. And underneath it here, it's actually floating on a bed of mercury, or a pool of mercury. So this thing is incredibly stable. And considering this was done in the late 1880s, this is quite a feat to be able to make this thing so incredibly stable. And it'll make sense in a second as to why this is sitting on a pool of mercury, and that will be in this slide. So if you guys remember the Michelson setup, so we had you guys in the lab build the Michelson interferometer, and the reason why it's called the Michelson interferometer is because it's named after these people who developed the Michelson-Morley experiment. So just like in your experiment, come up with some light. You have some light source. It has this partially reflecting mirror, bounces off of this mirror here and comes in to your observer. And then there's a second arm where it comes to this mirror and bounces back and comes to this observer. And because these will have some relative phase difference, you'll get an interference here. There will, of course, obviously be light going back to the light source, but we don't observe that, so we don't care. Now, how Michelson, why he developed this was that before this point, there was an idea that electromagnetic radiation had to travel in a medium, and they wanted to know what this medium was. So remember when we derived the electromagnetic waves, we saw that there was the speed of the wave was dependent on the permeability and permittivity of free space, and that is equal to 1 over c squared, which is the velocity of the light. And so this implied that there was some kind of medium that were dependent on these fundamental physical constants, and they didn't really know what it was, but they called it the ether, and it was just some medium that light traveled in, because water waves travel in water, sound waves travel in air. I mean, any vibration, you know, traveling through the floor or through a wall or something like that, that requires a medium. So they thought that electromagnetic radiation also required this electromagnetic medium, and they called it the ether. But it turns out that people started to realize quickly that then it mattered what you were doing relative to this velocity of the ether. And so what they had, what Michelson came up with, was this very stable interferometer that he could rotate. And so the velocity of the Earth, as it orbits around the sun, is something like 3,000 meters per second or something like that. And so from that means that as the Earth, you know, spins on its own axis and then revolves around the sun, we should be able to determine what the relative velocity of the Earth is relative to this, to the motion of the sun, or relative to the motion of this, to its ether. And then that way we can actually find out what this frame of the ether is, and then that should hopefully satisfy all of Maxwell's equations. So in one instance, we have it that this Michelson interferometer is moving in this direction relative to the ether. We have no idea if that's right or not, but we'll just pontificate, we'll just guess that this is true. And then if we can actually rotate this whole thing so that instead mirror A is up here, the light source is here, your observer is over there. But then that changes which mirror is going with the ether and which one's going orthogonal to the ether. And it turned out that if you rotate the experiment very carefully, the number of fringes you could see is going to be 2 times the length, so the length of this interferometer divided by the wavelength times v squared over c squared, where c is the velocity of the light. It turns out that I have some detailed notes here that I'll be posting, but it turns out that as typical of experimentalists, that when this is moving in this direction, that he accounted for the light coming here and coming back here relative to and the velocity relative to the ether is calculated correctly. He hadn't accounted for this arm actually should be moving this way, and so that means that the velocity or the time that it takes for this light to travel is slightly different than he thought. And so it ends up being off by a factor of 2, and Lorentz ended up finding the correction for that. And so, as typical of experimentalists, they're off by a factor of 2. And I can tell you, as an experimentalist, that's often true. Okay, so let's put in some numbers for this. If our wavelength of light here is about 500 nanometers, which is kind of like green light, slightly blue green light. The length of his table was 11 meters, and so, or the length of each of these arms was 11 meters. So, so it's quite a large distance. If the velocity of the Earth around the Sun is on the order of 30 kilometers per second, or 3 to the 10 to the 4 meters per second, that this gives a relative v over c is 1 times 10 to the negative 4. That we can actually be sensitive to 0.44 of a fringe, or half a wavelength, which is actually kind of ideal. That's kind of like the minimum sensitivity that you want. So that's why this thing needed to be this big. You need to have this thing this large. You wanted to use shorter wavelengths so that this was more sensitive. But you should be able to see this difference as the Earth is either traveling, with the ether or against the ether or whatever. But it turned out he didn't see anything. And so, as part of this correction, Lorentz said, well, instead of this path taking this time that you think it does, and this path travels the distance that you think it does, let's put in some correction factors to account for this null result. It's interesting, actually, when Michelson did the experiment by himself, he didn't have as sophisticated an experiment, and I think it took him, he did it like 6 or 7 years earlier. He saw an equivalent to one fringe difference with an error of 1. And so it was basically like, well, it could be 0, but it could be 1. And, the ether phenomena would predict 1, but special relativity would predict 0. And he basically was like kind of right in between. And so he said, well, this is inconclusive, and so it took him 6 or 7 years to actually, develop that more sophisticated slab with all that mercury to be able to improve the sensitivity. And then once he did, he improved his error bars, and he said, no, there is no result. And so with that, Lorentz took this experiment seriously and said, okay, well, what if we have these correction factors? So he didn't explain where these came from, but he does have these correction factors where this new time is related to the time that we think it should be, but then there's this 1 minus v squared over c squared to the 1/2. And the distance that this length of this arm is instead contracted by an amount, or it changes by an amount that's proportional to 1 over the square root of 1 minus v squared over c squared. So where this bar over t and this bar over x is in the moving frame, and we measure the time and this length in our frame, delta x and delta t. And then we can simplify this math because this is always going to be this gamma factor of 1 over the square root of 1 minus beta squared. Beta is v over c, this velocity relative to the speed of light. And so we can actually jump from our frame to this moving frame by having this correction factor and then t minus v over c squared over x. And we can also have this length changes, this position changes by the gamma factor times x minus vt. So if we think about how Galilean transformations should work, of course, our frame should have the same time as the moving frame, and so this v over c squared, this is going to be 0, and this gamma is going to be equal to 1. So our time that we measure is going to be the same time that somebody else measures who's moving relative to us. And if we're measuring some position, the position that we measure is going to be this, but if something's moving relative to us, so say somebody's on a train or a boat or a car or a plane that's flying by us, this gamma factor is going to be equal to 1 in a Galilean transformation. But our position, the position that they see is going to be our position minus this relative velocity times the time. And so this is consistent with Galilean transformations, but now with special relativity we have this gamma factor. And it's the orthogonal directions are actually the exact same as they were before. So using this notation, we can actually go from our frame that we have here, this r time and x, y, z, to this moving frame in this t bar, x bar, y bar, z bar, through this transformation matrix. And this is the Lorentz transformation matrix. So I want you to become familiar with these 4x4 matrices because we'll be using this and also tensor notation for the remainder of the course as we're talking about special relativity and electromagnetic phenomena in the context of special relativity. And that'll be it for today's lecture. I'll be uploading handwritten notes on this material. If you have comments or questions, you can leave it in the comments on the YouTube channel, or feel free to email me. Hopefully this is working well for you. Please also let me know if this is suitable for you, or if you want this to be in better detail, or if I can make any changes so that you can learn this to the best of your ability. And I'll be posting more notes next week on Tuesday when we continue on special relativity with electrodynamics. See you then.